All right, today we are taking on perimeter and area in the coordinate plane. I wanted to start us off with a little review of slope, midpoint, and length of a segment. So we're given segment AT, we're given the two endpoints, and we want to find slope, midpoint, and length. All right, so let's start with slope. So slope we know is change in y over change in x, the rise over the run. So if we want to think of it as a formula, y2 minus y1 over x2 minus x1 is perfectly fine. If I wrote that as y1 minus y2 over x1 minus x2, totally fine also. So now, if I look at the y values first, I can take negative 5 minus 3 divided by 2 minus negative 6. So on top I have negative 8, and on bottom I have positive 8, because when I subtract a negative it goes to a positive. So negative 8 over positive 8 is negative 1. So I know my slope is negative 1. Okay, next, midpoint. So midpoint is average of x, average of y. So I'm taking my x values, adding them, and dividing by 2. I'm taking my y values, I'm adding them, dividing by 2. So here when I plug in, I have negative 6 plus 2 over 2, and 3 plus negative 5 over 2. Okay, so now I have negative 8 divided by 2. I'm sorry, did that wrong. Negative 4. Let me crunch that correctly. I have negative 4 over 2. And then over here I have 3 plus negative 5, so I have negative 2 over 2. Okay, so negative 6 plus 2, negative 4. Negative 4 over 2 is negative 2. And then negative 2 over 2 is negative 1. So my midpoint will be negative 2, comma, negative 1. So this is the x-coordinate that should be right smack in the middle of negative 6 and 2. This is the y-coordinate that should be right smack in the middle of the 3 and negative 5. So negative 2, negative 1. Okay, and then length. Length is the same as the distance formula, or you can visualize it as a right triangle. That's okay too. So a big square root, difference between the x values. Again, the order doesn't matter. So I could write this as x1 minus x2, for example, or I could write that in reverse. So difference between the x values squared plus difference between the y values squared. So there's my formula. If you like the formula, that's what you're going to plug into. So when I plug into that, difference between the x values, so negative 6 minus 2, order doesn't matter, and then squared, plus difference between the y values, so 3 minus negative 5 squared. So right now I have negative 8 squared plus positive 8 squared. Okay, I'm going to keep working over here just so you can see my paper trail. So now in my next stage, I have the square root of 64 plus 64, right? Negative 8 squared plus 8 squared. So when I add those two 64s up, I have the square root of 128. And I'm trying to simplify that, and I know that that was 64 times 2. And 64 gives me a beautiful pair of 8s right there. So I know that that's going to simplify to be 8 root 2. So my length is 8 root 2, or 8 times the square root of 2. All right, so a little refresher on slope, midpoint, and length. So now looking ahead, looking at perimeter, which I'm guessing most of you have heard of before. So perimeter is the total distance around a figure. We can think of it as the sum of all of the sides. Let me give you a visual. So here I picked a rectangle because it's a really good one to visualize. So right here I put my rectangle on the coordinate plane. So I could see that I have 6 units and then I have 10 units like this. So the horizontal is 6, the vertical is the 10. So my base is 6, my height is 10. So my perimeter here, I just be adding up all of my sides. So 6 plus 10, 6 plus 10 would get me 32. So my perimeter here would be 32 units. And then my area is the total number of non-overlapping unit squares that cover a figure. So I've drawn it out like this so you can see exactly what those unit squares look like. So I should see 60 of them because it's 6 by 10. 6 times 10 would get me 60 of these unit squares. So my area would be 60 units squared. All right, so area of a rectangle, like I already established, would be a base times height. So area is base times the height. Okay, in a rectangle, we're going to talk a whole lot more about the rectangle, but what I want you to know right now is that it's a type of parallelogram. I always write p-gram just to abbreviate. So it's a type of parallelogram. A parallelogram has 2 pairs of parallel sides. Okay, with all of the interior angles that are congruent, they're all 90 degrees. So it's a parallelogram with congruent interior angles. They all are 90 degrees. So for my rectangle, let me show you that little box notation that means right, like that. So a rectangle is a type of parallelogram. So that means that both pairs of opposite sides are parallel and all of the interior angles, they are 90 degrees. Okay, so then if I'm labeling my base and my height, I've just drawn my rectangle a couple of different ways. So here would be my base. And here would be my height. Okay, for this one, this would be my base, and this would be my height. Okay, a square, well, a square is also a type of parallelogram, also has the properties of a rectangle, so it shares that all of those interior angles are 90 degrees. And it also shares a property of a figure called a rhombus. We'll talk about that a little bit later on. And a rhombus has all congruent sides as well. So the area of a square, it's going to be the same as the area of a rectangle, base times height. But since all those sides are the same, we could also say it's just a side squared. So we have some options here for the square. So I'll write it as area is base times height. Or area is a side squared. So a side times a side would be a side squared. So here I'm going to remind you that it is a type of parallelogram first. Okay, with congruent interior angles. So all 90 degrees also. So it shares that with the rectangle and congruent sides. Okay, so all sides are congruent. So here I'm going to show the little box notation for the right angles. And then all of the sides are the same too. So I'll give that a tick mark. So here is my square, a type of parallelogram that shares this property of the rectangle. All of those interior angles are congruent, 90 degrees, and all of the sides are congruent too. It shares that with the rhombus. Okay, and so if I label this my base, then here would be my height. So again, a base is the same as the height when it's a square. So that's why that second formula, a side squared, also works. Okay, next we're going to look at the area of a triangle. I want to look at different types of triangles, and before I tell you the formula, I want you to visualize something. So let me slide this up. So area of a triangle, that's our focus. So I'm going to start with a rectangle. So this yellow rectangle right here is just my starting point. I'm going to overlay a triangle. So here is my triangle right here. So my triangle, my model in blue, has the same base length and the same height as the rectangle. And I'm trying to figure out, well, how is its area related to that rectangle? I have a few guesses. I'm sure you do too, just by looking at it. But I wanted to show you something specifically. So what I've drawn in with this triangle, I've made this the base. And if I rotate my triangle, I could really make any side my base. I've just chosen to do this one. So this is my base. So if this is my base, that perpendicular segment that connects my base to my vertex right here, this is my altitude. Sometimes we call it the height because we're thinking of what its measure is. So looking here, here is my base. This is the altitude, that perpendicular segment that connects the base to the vertex right here. And its measure right here would be the height. Okay, so if I take here these little green triangles, I'm just going to overlay it like this just to show you that it matches perfectly. So what I've done is I've taken that big triangle and I split it down where its altitude was right here. So I've divided it right down there and I've made it two triangles, two smaller triangles. And what can happen when I rotate this one, if I rotate it 180 degrees, it can lock in right here and fill up all of that empty space right there. And if I rotate like this for the other one, another 180, I can fill that empty space up there. So what I'm able to see is that, well, two of these triangles would fill up that space of the rectangle right there. So that tells me that my area will be 1/2 the base times the height, right, of a rectangle that shares the same base and the same altitude, the same height right there. Let me pull that away. Okay, so here I'm saying area of a triangle is going to be 1/2 base times height. Okay, and I've drawn triangles a whole bunch of different ways. So I've drawn an acute triangle, for example. So in my acute triangle, if I make this my base, let me mark that here in purple. So if this is my base, then my height would be that perpendicular segment that connects the base to the vertex. So right here with my acute triangle, this would be my height, just like that. An acute triangle, all of the angles are less than 90 degrees. Okay, in an obtuse triangle, let's say that I make this my base. In an obtuse triangle, you have one angle that is more than 90 degrees. So here, if I try to draw my height, so here's the vertex. If I'm calling this my base, let me make sure I write B next to that. So if I make that the base, I'm looking for the perpendicular segment that would connect the vertex to the base. So the way that I've drawn this obtuse triangle, that's a little tricky. So what I need to do is I need to extend the pathway of my base. And then draw in that height that would connect to it. So here would be my height. So for this model right here, my base is still only from here to here, and my height is still that perpendicular segment that connects the vertex to that pathway of my base. Okay, for a right triangle, this is our easiest variation. We love it. Here, this leg is our base, and the other leg is the height. So those two perpendicular segments, here and here, the two legs end up being the base and the height when it's a right triangle, when you have exactly one angle that is 90 degrees. Now I've said a few of these things, so let me just add it to our notes. So for an acute triangle, all angles are less than 90. So for an acute triangle, all angles are less than 90. For obtuse, we have one angle that is more than 90. Okay, a right triangle has one angle that is 90. Okay, so far we're caught up. All right, so next we're looking at an isosceles triangle, and an isosceles triangle has two congruent sides. So let me mark that here and here. So two congruent sides, and technically we'll define this later on, it's two or more. So I'm drawing a model where it's exactly two. So here's my isosceles triangle. Here is my base of it, at least how I'm drawing it. Here's my base, and then my height would be that perpendicular segment that connects my base to that vertex. So here is my height. And one thing that's useful to know here is that that height, that segment, is splitting our isosceles triangle into two congruent right triangles. So splits into two congruent right triangles. Okay, and then lastly, an equilateral triangle, that means that all of the angles are the same. I'm sorry, all the sides and the angles are all the same. Let me say that one more time. So equilateral, all the sides are the same, all the angles are the same. So all sides are congruent, all of the angles will be 60 degrees. And if I draw in, here is my base, and here is my height. It does the same thing as the isosceles triangle. It's going to split into two congruent right triangles. And that's because an equilateral triangle is isosceles. It has those two congruent sides. So it just for equilateral, it has all three of them, not just the two. So this one splits into two congruent right triangles, and more specifically, we'll learn this a little bit later on, those triangles would be called 30, 60, 90 triangles. So this angle would be 60, this would be 60. This angle up here is being bisected. This would be 30, this would be 30. But again, we'll talk about this later on in the semester. So here I'm just going to write splits into two, let's see, I'll write it here, two congruent 30, 60, 90 triangles. So splits into two congruent 30, 60, 90 triangles. And like I said, we'll talk about this a little bit more later on. What that looks like if I just draw one of them, here would be the let's see, there's the 30 and here's the 60. Let me pull away so you can see that. Okay, so here would be the 30 and here would be the 60-degree angle. That box notation would be the right angle. So that's a 30, 60, 90 triangle. All right, next up, I want to graph this triangle, and then I want to find the perimeter and the area. So F is at -3, -2. So -3, -2 right here. O is at 0, 6. So right here. And X is at 3, -2. So 3, -2 right here. So let me connect my dots and label those vertices. Okay, so here is my beautiful triangle where this was F, here was O, and here is X. Okay, so find perimeter and find the area. Okay, so if I sketch it off to the side, let me just make a little model to the side. Here is my figure. And what I can see right now is that this is an isosceles triangle. I can see that because right here is a line of symmetry. I can see that this triangle here would reflect over that line onto this triangle over here. But I can still check that with my math. So if I look at FX, that's a horizontal segment. That's not tricky. I can see that that's 6 units apart. Okay, if I'm looking at this segment here, FO, I could use the distance formula. So if I use the distance formula, here's my big square root, and I'm looking at the distance from F to O. So I'm focusing on these points. So if I look at the difference between the x values, so -3 minus 0, and then I square it, and then the difference between the y values, so -2 minus 6, and then I square it, then right now I'm at -3 squared, and here I'm at -8 squared. So I have 9 plus a -8 squared is 64. Okay, so I have 9 plus 64, which will get me 73. And 73 is not going to simplify, so I'm just going to leave that as is. So this measure is square root of 73. Okay, so then if I'm looking at OX as well, let's say I do OX right over here. Let's say that I do that a different way. So let's say that I'm picturing, I'll draw it in, I'm picturing this right triangle right here. So if I picture that right triangle, I'm trying to find the hypotenuse. Let me draw that. I'm trying to find the hypotenuse. So if I look at what's this span, that's 3 units. And then what's that vertical span? Here I was at 6, and down here I'm at -2. So I'm 8 units right there. So then I can see, okay, we'll take the square root of 3 squared plus 8 squared. Square root of 9 plus 64, I'm going to see the same number show up, that square root of 73. Okay, so I've found all of my sides now. So my perimeter, I just have to add them up. So 6 plus the square root of 73 plus the square root of 73. These are like terms, they can combine further. I have 6 plus 2 square root 73. That would be my perimeter, 6 plus 2 root 73 units. Okay, and then area, well, since I can see that vertical segment right here that would connect my base here to that vertex right there, let me draw it in just like so. There's that vertical segment right there. There's that right angle. And I can see that it is, here's 2 units. Okay, and then here's 6 units. Here is a height of 8. So since it was vertical, I could just count it up. So if I'm looking at my area, I'm looking at 1/2 base times height. So I'm looking at half of 6 times 8. So half of 6 is 3. 3 times 8 is 24. So my area would be 24 units squared. Okay, so there's my example with triangle FOX. Okay, flip the page. Turn to that second sheet, please. And here we go. So find the perimeter and area of the polygon graph with the given vertices. So first off, what kind of polygon are we looking at? Right? So far we've only covered triangles, rectangles, and squares. So let's hope it's one of those options. So this should be a rectangle. Let's just double check. So to be a rectangle, we know that we need to have opposite sides that are parallel. Well, if I check slope here, down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, their slopes will match. These slopes will both be -1. Okay, up here, I'm going up 1, right 1, up 1, right 1, up 1, right 1, up 1, right. These slopes are going to match too. The slope will be +1. So these slopes are -1, these slopes are +1. So I can tell that I have opposite sides that are parallel. And since 1 and -1 are opposite reciprocals, that means that I have right angles in each of these slots. So let me write that out. So it is a rectangle because we know that all of these angles are right angles. Okay, we know that all of the interior angles are 90 degrees because we have perpendicular segments. Okay, we also saw that opposite sides are parallel too. Okay, so I'm going to draw in a little box notation just to show that this is a rectangle. So then I need to find my sides, and I know that my opposite sides are going to match. So let's say that I focus on SP first. Let's find this side, SP. Okay, if we like distance formula, that's fine. If you like to picture the right triangle, that is fine too. I'll do one of them with the distance formula and one of them using the right triangle technique. All right, so distance formula. So if I'm looking at SP, here are the coordinates of SP. I have them plotted as well. So difference between the x values, I have -2 minus 1, and then squared. Difference between the y values, so 5 minus 8, and then squared. Okay, so now -2 minus 1, and then squared, so I have -3 squared. And then 5 minus 8, also -3, -3 squared. So square root of 9 plus 9, which is 18. So I'm taking the square root of 18, so I have 9 times 2, and here a pair of 3's. So SP is 3 root 2. So I know that right here is 3 root 2, and right here is 3 root 2. Let me add that to my picture. I might redraw it down below just to see it more clearly. So let's say that I draw that here. So here is 3 root 2, here is 3 root 2. Okay, so then I want to get to PO and ST. I want these two opposite sides. So here, let's say I use that right triangle technique. So what I'm picturing is I'm picturing this right triangle right here. Okay, let me write out that I'm solving for PO. So if I picture that right triangle where I'm solving for the hypotenuse, here I have 1, 2, 3, 4, 5, 6 units horizontally, and I'm going to have 6 units vertically. So 6 and 6, just like that. So then I'm looking at the square root of 6 squared plus 6 squared. So 36 and 36, which makes 72. Okay, 72 is 36 times 2. So I get a pair of 6's, which leaves me with 6 root 2. So I have 6 root 2 and 6 root 2 for these opposing sides as well. I can add that up here. I just don't know if you can see that as clearly. And then we're good. Okay, so I have all of my sides, but I want perimeter and I also want area. So for perimeter, we're going to add up our sides. So we're adding the 3 root 2 and 6 root 2, 3 root 2, and 6 root 2. And all of our radicands match, so we can combine 3 plus 6, 3 plus 6 is going to get me 18 root 2. So my perimeter is 18 root 2 units squared. Okay, and then for area, it is a rectangle, so base times height, and our base here would be 3 root 2, and then the height would be 6 root 2, and that's what I'm multiplying. So I have 3 root 2 times 6 root 2. So whenever I multiply a square root of 2 by a square root of 2, it's going to give me a pair of 2's underneath the same radical. So it unlocks to be just 2. So this ends up being 3 times 6 times 2. 3 times 6 is 18, times 2 is 36. So my area would be 36 units squared. All right, next up. Find the perimeter and area of the triangle that is bounded by the system of equations below. So here I have three equations. So I'll use different colors just to show three different lines. So y minus 2 equals 1/3 of x plus 4. So I need to recognize that that is in point-slope form. So I need to know what is my point and what is my slope. So my point would be -4, +2. And my slope would be 1/3. So I'm going to drop my anchor, plot a point at -4, 2, right here. And then my slope is 1/3. So up 1 and right 3. Up 1 and right 3. I'm just going to give myself a few more points and then connect the dots. All right, so there is my first line right here in red. I'll label that that's the first one. Okay, and then the second one, x equals -7. Well, x equals -7, that's a vertical line. So for all values of y, x stays constant at -7. So right here in purple, that will be line 2. Okay, and then the third one, y equals 5. So y equals 5. So for all values of x, y is constant at 5. So right here will be that last line in green. Okay, 3. So let me shade it so that we can see clearly what that triangle looks like. Okay, and then I'm also going to just sketch it out off to the side as well. So I see that it's a right triangle because I have a horizontal and a vertical pathway, and any horizontal and vertical pathway will always make a right angle right there. So then I can see that this spans 4 units apart. Okay, and then here to here, if I count that out, so I'm 7 to here and then 5 over, so I have 12 units right here. So if I want to solve for this last side right here, I can use the Pythagorean theorem, right? I'm finding the distance from this point to this point, so I could technically use distance formula too. I think this is easier. So big square root, I'm just doing it a little shorthand, 4 squared plus 12 squared. So now here I see, okay, 16 and 144, which is 160. And then I know that's 16 times 10. Here's my beautiful pair of 4s, no pair of the same in 10. So 4 root 10 right here. Okay, so I know all of my sides. So if I'm doing the perimeter, I'm just adding the 4, the 12, and the 4 root 10. So I get 16 plus 4 root 10. So perimeter is 16 plus 4 root 10 units. Okay, and then I need area as well. So area would be 1/2 base times height. It's a triangle. So half of, when it's a right triangle, the 2 legs are the base and the height. So the 2 perpendicular segments. So the 4 and the 12. So half of 4 is 2 times 12 is 24. So my area would be 24 units squared. Okay, one more example. Thanks for hanging in there. Okay, so here I also have 3 lines, so I have to graph those first. So my first line here is in slope-intercept form. So my y-intercept is at 0, 4. And my slope is -1/2. So I'm going down 1 and right 2. Just plotting a lot of points along this pathway just to see things clearly. Okay, so here we go. Here is that first line. Okay, and then the second one I will do in purple, also slope-intercept form, also the same y-intercept. My slope here is -3, so I'm going down 3 and right 1. Down 3, right 1. Down 3, right 1. Okay, so here we go with the next pathway. Okay, and then the last one here, that one is in standard form, so it's going to be easier to get the x and y intercepts. So x-intercept, we know that that's when y is 0. Y-intercept is when x is 0. So if I plug in 0 for the y, okay, block that out, solve for the x, x would be 3. So the x-intercept would be at 3, 0. Okay, y-intercept is when x is 0. So if I plugged that in and covered that up and solve for y, I would get -6. So 0, -6. Just like that. So I'm going to plot a point at 3, 0 and 0, -6 right there. And then connect my dots. And then here is that third line right there. So then if I shade it in, I'm looking at this triangle right here. Okay, and one thing that I notice is that this is also a right triangle because this line has a slope of -1/2. This line has a slope of 2. So I know that these pathways here and here, they are perpendicular. Their slopes are opposite reciprocals. So let me off to the side do a little sketch of this triangle. Okay, so there is roughly what that triangle looks like, and I need to figure out what all of the side lengths are. So since we're running out of time, I don't want to go too long, I think I'm going to skip to just what those side lengths are going to be. So we know how to find them. So this side would be 2√5. This side will end up being 2√5. And then this side will be 2√10. So again, distance formula or just Pythagorean theorem will help you get to those values. Okay, so I recognize it's not just a right triangle, it's an isosceles right triangle because I have these two sides that are the same. So now if I want to get to my perimeter, I'm just going to add up my sides. So I have 2√5 plus 2√5 plus 2√10. These are like terms, so I can combine them, and I get 4√5 plus 2√10. So my perimeter is 4√5 plus 2√10 units. Okay, and then my area, 1/2 base times height. So here, if I make my legs my base and my height here and here, and plugging in the 2√5 and the other 2√5. So this is like saying 1/2 times 2 times 2. √5 times √5 is just 5. So if I take half of 2, that's 1. Times 2, I'm back to 2. Times 5, I'm at 10. So my area is 10 units squared. Okay, one other little fun thing I want to show you. I don't actually have to look at this as a right triangle. Let me draw it another way. Put a little star over here. So if I draw that triangle out just one other way. Okay, so I'm drawing it out again. I know it's a right triangle, but it's also an isosceles triangle. So I know that if I connect this vertex to this base, let's say that I call this my base, which I know is 2√10. If I look at that perpendicular segment that would connect here, this base to this vertex, then this right here would be my height. Okay, it's just another way of looking at it. It's connecting this point right here to this point right here. That's what I'm looking at. And that measure is root 10. So if I solve it this way, and I say area is still, well, 1/2 base times height, and I plug in that 2 root 10 for the base, and that root 10 for my height like this, watch what happens. This is like saying 1/2 times 2. The root 10 times root 10 is just 10. Half of 2 is 1 times 10, and I'm back to 10. So I'm getting there a different way. We're going to see that there's several different options for capturing area of triangles. And I'm trying to show you lots of different varieties to help you just feel more confident in how to get to area overall. All right, have a good rest of your day.